Okay, let's talk about a new topic, something called pKa. Now look at this question, spend a little bit of time reading it, and then we'll try and go through the answer together. Okay, so hopefully you've read the question. What I want to do is I want to focus a skill that you need for your exam. When you're writing an exam and you see a long stem like this, especially for the USMLE exam, look at the last sentence first, because what that's going to do, it's going to focus your attention. Now, in this particular question, the last sentence says that it has a pKa of 3.8 and what percentage of the drug will be hydrophobic. Well, all of a sudden you've realized that the first half of that question is completely useless to getting your answer. So you can actually just ignore a lot of that clinical information and get to the answer much quicker. So now what we do is we want to pick between the answers, 100%, 50%, 10%, and 1%. So what percentage of the drug will be hydrophobic at a pH of 4.8 if the pKa is 3.8? Well, what is pKa? Let's go over that together. So aspirin has a pKa of 3.8. So what is pKa? The pKa is that pH level at which a drug is 50% protonated and 50% non-protonated. So the ratio of protonated and non-protonated forms is 1:1. For weak acids, and you can see that because the pKa is 3.8, which is less than 7, that's an acid. So for all weak acids, the ratio changes to 1:10 or 10%. At 1 pH unit, more alkali than the pH, and the ratio changes to 1:100 or 1% at 2 pH units. So remember that pH is a logarithmic, so 1 unit is 10, 2 units is 100, 3 units is 1,000. So if you have a pKa of 3.8 and the pH of 5.8, you've got a pretty significant difference in ratio, so 2 pH units is 1:100. So let's take a look at pyrimethamine. Pyrimethamine is another drug that has a pKa of 7.42. That makes it a weak base, right? Because the 7.42 is actually higher than 7.0, so anything above 7.0 is a base. The pKa is the point at which a pH that gives you 50% protonated and 50% non-protonated drug, so the ratio is 1:1. For weak acids and bases, the ratio changes by 1:10 or 1:100 for each 1 or 2 pH units you are from your pKa. Now, because it's a base, the more alkali the pH is, it makes it less soluble or less polar in the protonated form. So to go over it again, for weak bases, they are ionized, they are more polar when protonated and more soluble when protonated. With weak acids, they are not ionized, they are less polar when protonated and less soluble when protonated. That's really hard to remember, so I have a mnemonic for you to memorize this. There's BIPs and there's PAN. So bases are ionized, polar, protonated, and soluble, and PAN means that protonated acids are non-ionized, non-polar, and non-soluble. So if you remember these two acronyms, that'll help you with some questions. So speaking of questions, let's go back to our question in our case. The ratio changes from 1:1 to 1:10 at 1 pH unit more alkaline than the pKa, and it changes to a ratio of 1:100 at 2 pH units that are more alkaline than the pKa. So in the case of this question, we were saying the bottle label says that the substance has a pKa of 3.8. What percentage of the drug will be hydrophobic or lipid-soluble or lipophilic in the small bowel at a pH of 4.8? Well, what's the answer? So the answer is C, 10%. 1 pH unit difference, 10%, 1:10 ratio. Now, why do you care about a pKa? This sounds like a lot of chemistry that you left behind in pre-med. Well, the reason why we need to know this is because we need to know how to enhance excretion of a toxin. So, for example, an aspirin overdose, we want to alkalinize the urine. When we alkalinize the urine with sodium bicarb, We trap the aspirin molecules in the urine so it can't get reabsorbed back into the body. That's how we treat an aspirin overdose. It's also useful when we want to design a drug and when we want to mix medications. So in the pharmacy world, it's also something that's very important.